Hello, it's Helen Dakin, and I'm back to discuss with you solving for the number of payments in ordinary simple annuities. When you're solving for the variable, any of the variables in an ordinary simple annuity, you need to determine, first of all, whether the future value or the present value formulas are applicable. So you have a description of a financial problem, and you know the size of the payment, and you know the nominal interest rate in the annuity, and you also can figure out the number of payments. The question is, when you're given an amount, is that amount the present value or is that amount the future value? And it depends in this particular case on the context, the description of the problem. So from the description of the problem, you should be able to determine whether you have been given the present or the future value. You will note that the BA2 Plus calculator has several functions that are built in to help you solve these financial problems. First of all, the PV function is built in. Under PV stands for present value, FV for future value, PMT for payment size, and N represents the number of payments. If you are trying to solve a problem for the number of payments, you will have to use compute N or CPT-N. IY is the nominal interest rate compounded C periods per year, and it's very important that you note that CY is the number of periods per year, compounding periods per year, and PY is the number of payments per year. For an ordinary simple annuity, the number of interest periods per year and the number of payment periods per year coincide. So when you're solving for the number of payments, if you know the present value or the future value, that's the value that you will be entering into the calculator. And remember that the signs will always be different. The signs will be opposite. So if the present value is positive, the payments will be negative. If the present value is negative, the payments will be positive. Let's begin by taking a look at the first example. How many deposits of $3,000 at the end of each semi-annual period are needed before a total of $100,000 is accumulated, assuming that the rate is 10% compounded semi-annually? Let's begin with the time diagram for this problem. We know that we are making semi-annual deposits of $3,000, so we'll show that 0, 1, 2, 3 semi-annual deposits of $3,000 at the end of every semi-annual period. That represents an ordinary simple annuity because the payments are made at the end of every period. We don't know how many deposits there are, so we'll use N for the number of deposits, and we'll draw an annuity bus around that. So we've got $3,000 every 6 months. So there's our annuity, ordinary simple annuity, where we don't know the number of payments. We also have an amount of $100,000, and it says here that the total of $100,000 is accumulated at the rate of 10% compounded semi-annually. So I know that the interest rate, the nominal interest rate is 10%, and it's compounded twice yearly. So we've got an I value of 5%, 10% divided by 2, or 5% per 6 months. So where does the $100,000 fit in the time diagram? Well, we need a total of $100,000 to be accumulated. So what that means is that I want to have a final value or a future value of $100,000. So I'm going to place that amount on my timeline at the back end of my annuity or on the future. So what that means is that my focal date is in the future, and that $100,000 represents the future value, the final value of the annuity. So I think we're pretty much on our way to solving this problem. We know that the only formula that is relevant here is the final value formula. So we're going to state that $100,000, the final value, is equal to the payment size, $3,000, multiplied by the final value factor, 1 plus 5% per 6 months to the power of N minus 1 divided by 0.05, 5% per 6 months. And so our problem is to solve this particular equation for N. So how do you solve this particular equation for N? Well, I guess the first thing that you could do is to divide both sides by $3,000. So we've got $100,000 divided by $3,000 is equal to the annuity factor, which is 1.05 to the exponent N minus 1 divided by 0.05. Now, what is $100,000 divided by $33,000. That works out to a number of exactly 33.33 or 33 1/3. So let's make a note of that. 33.3 is equal to 1.05 to the n minus 1 divided by 0.05. Now for a moment, what I would like you to do is to stop and ask yourself the significance. What is the significance of the 33.33? What does it mean? What have you actually calculated? By dividing by 3,000, what you've actually done is you've determined that 100,000 divided by 3,000, that's the 33 is the minimum number of deposits that would be required if no interest was earned on the account. So if you were putting the money in a shoebox, then it would require 33.3 deposits of $3,000 to amount to $100,000. It would take 33 deposits to accumulate to $100,000 if there was no interest being earned. So what does that tell you about N, the number of deposits? What this tells you is that since interest is being earned, in fact, an interest at 10% compounded semi-annually is being earned, what that tells you is that the number of deposits N is going to be less than 33 1/3. Definitely, because we're earning interest. The interest rate is more than 0%. So the number of deposits will be smaller than 33. Well, let's carry on. In order to solve this equation, the next thing that we're going to do is we're going to multiply both sides by 0.05. So 33 1/3 multiplied by 0.05. And remember, don't clear your calculator at all. Always retain all the digits. So you multiply that by 0.05 and you'll be left with the numerator of this right-hand side. So 1.05 to the n minus 1. And we've got 33 1/3 multiplied by 5% ends up being a value of 1.66 repeating, or 1 2/3, and that's going to equal 1.05 to the exponent n subtract 1. Now we're trying to solve for n, so we need to isolate the term containing the n variable, so we're going to add 1 to both sides of the equation. 1.66 repeating plus 1 is 2.66 repeating, and that's equal to 1.05 to the exponent n. At this point you have to solve for n, and the only way to solve for n is to use logs, so we will log both sides of the equation. You can use common logs or natural logs, so we'll have ln of 2.66 repeating is equal to n times the ln of 1.05, and so n will equal to the ln of 2.66 repeating divided by the ln of 1.05. So at the end of the day, this means that, or this works out to an n value of 20.103. So the number of deposits is 20.103. And these are going to be semi-annual deposits. And of course, it doesn't make sense. We can't have 0.103 deposits. So we are either going to have 20 deposits or 21 deposits. So what we'll do is we'll say we'll have 20 full deposits of $3,000 every 6 months, and maybe a 21st deposit that will be a little bit smaller. Let's determine the size of the last deposit, or if one is even necessary. Let's take a look and see what happens. So we know that we need at least 20 deposits. Let's figure out what happens after the 20th deposit. So we've got a time diagram here, and we'll show the 20 semi-annual deposits. That's 10 years worth of $3,000 semi-annual deposits. In fact, that's a total of 20 times 3,000, or $60,000 in deposits. And we know that definitely at the end of the term of this annuity, after the 20th deposit, we will definitely have more than $60,000. How much more? Well, we can do that, answer this question by determining the final value of those 20 deposits. So let's do that right now. We've got the final value of those 20 deposits is going to be $3,000 per 6 months multiplied by the annuity factor 1 plus 5% per 6 months, 20 semi-annual deposits minus 1 divided by 0.05 per 6 months. And that calculates out to a final value that is equal to $99,197.86. So leave that number on your calculator. So that's $99,197.86. And that's going to be the amount that you have at year 10 or at the 20th deposit. So we've got 99,197.86 after the 20th deposit. So, well, we're a little bit short. Our goal was $100,000, so we seem to be about $802.14 short. How do we make up for that shortfall? Well, let's see what happens if we let that money sit in the account or in the investment for another period. And so the question is, how much would it be worth 6 months later? So in other words, let's take that amount of 99,000 and add interest to it for one more period. So how do we do that? Well, we're going to multiply that by 1 plus 5% to the power of 1. We're just going to compound that by one more interest period. So now we're going to say, let's take the focal date and move it one more interest period later down the road. So after 6 months, we will have 5% more in interest. And so that maturity value will be $99,197.86 multiplied by 1 plus 5%. When I add 5% to that amount, I end up with a maturity value of $104,157.76. I'll round that off to the nearest penny. What does this tell you? This tells you that you don't need a 21st deposit because you're actually $4,000 over your target of $100,000. So a 21st deposit is not needed, because we've already reached our goal.